But what is it that's wave? What is going on? You have a, let's go back to hydrogen. You have a proton and an electron going around it. What is waving inside the electron? It's not an electromagnetic wave, right? A photon, we said, when we have a wave packet like this, the thing that's going up and down can be thought of as the electric field and the magnetic field at that point in space. But what about in a hydrogen atom? What is the electron doing? What is it that wave function psi represents? And it turns out it's actually a wave of probability. That it's the probability of finding the electron at that point in space at that moment. Okay, in order to be precise, probability density, because probability of finding it at any particular point goes to 0. But how much probability per unit volume are you talking about is what the wave function corresponds to. That's a kind of a bizarre thing. What does that mean, probability? Where is it? It's either somewhere or it isn't somewhere, right? I mean, that's how we're used to thinking about real things in real physics. Actual position and a location and a momentum and a velocity. It's all like, billiards, right? Well, in quantum mechanics, not so. All we can talk about is that, well, for that wave packet, it's kind of there, and it kind of has that momentum, and it's traveling at a certain velocity or whatever. But where is the particle? Well, it's sort of spread out. It's smeared out. We've smeared out its position and smeared out its momentum in a way that is wave-like. It has a wave nature. It still has kind of a location and kind of a well-defined wavelength, but it's not perfectly known. Well, if you get into the mathematics, that wave function is actually described by best described by complex numbers with real and imaginary, square root of -1 components. But that's, well beyond the scope of this course. Now, it turns out in quantum mechanics, there are observables like position and velocity, momentum, and so forth. But if you take pairs of these observables, they're connected by the Heisenberg uncertainty principle in the following way. Too often, the Heisenberg uncertainty principle and quantum this and quantum that are mischaracterized, meaning, oh, you can't be certain about anything or nothing certain. Not true. Not true. All it's saying, all the Heisenberg uncertainty principle says is that you cannot simultaneously measure the position and momentum of a particle with joint precision better than h bar, Planck's constant, divided by 2 pi, divided by 2. For deep reasons that fall out of the mathematics. And Heisenberg was the first one to enunciate this. So what does this mean? Delta x might be the precision with which you can say that particle is at point x. So it's at x plus or minus a little bit. And it has a momentum p plus or minus a little bit. Now, it doesn't say that you can't measure it really, as precisely as you want. You can make delta x as small as you want. But there's a cost to pay, and the cost is that delta p then becomes large. So in other words, if you measure really precisely the position of a particle, you lose information about its momentum. Likewise, if you measure its momentum really precisely, you can't tell where it is in space. So this product is maintained. Now, like I say, I think Heisenberg's uncertainty principle gets a little bit abused into extrapolating that, oh, quantum mechanics tells us that we can't say anything for certain anymore. It's really not like that. That's more philosophy and even sort of pop philosophy rather than real philosophy. And really, it's a statement about measurement and what measurements you can do. It is kind of, it's a sensible thing in the following way, that if you're going to do a measurement of the position of a particle, you're going to completely destroy any information about its momentum, and vice versa. That kind of makes sense. There's no measurement that you can do that doesn't change something, even something as simple as, let's say, taking the temperature. Suppose you have a cup of water, it's hot, and you want to measure its temperature. What do? You take a thermometer and you put it in there, right? And then the thermometer tells you what it is. 67 degrees centigrade. Is that the temperature of the water before you put the thermometer in? No. Why? Because a little bit of the heat from the water went into the thermometer to measure it. So you've disturbed the system. That's maybe a trivial example. But when you actually get into measuring the position and momentum of an electron, even in an atom or in space, you have to disturb it in some way to measure its position. You have to make it hit something, or you ultimately destroy it. Now that's more of a deep thing, and that's philosophy. That kind of philosophy is on the right track because it's telling you how to interpret the Heisenberg uncertainty principle in a meaningful way that connects with how we actually do measurements in the real physical world. The thing is, h, this value h is so small that you almost never run up against these sorts of effects in your everyday experience. Now, we can demonstrate quantum phenomena on macroscopic scales. We did so in the room here. We are able to take these gas discharge tubes, look at the spectrum of radiation coming out from them and see that there's very discrete, very well-defined allowed energy levels within these atoms for whatever the reasons happen to be. So we can see quantum effects on macroscopic scale, but if you tried to really measure very, very precisely those spectral lines, you would find that they actually have a little bit of a width to them. That width corresponds to an uncertainty in the momentum of the electrons in their orbits around atoms. So you can't probe it any better than that. Now, one of the interesting questions that we didn't address so far is, okay, you have this hydrogen atom, right? It's got a proton, there's an electron going around. Why is this, why is the electron, which is attracted to the proton, why doesn't it just radiate away its energy and fall completely into the nucleus, into the proton? Why do we have stable hydrogen atoms at all? It actually, one explanation of that is that the uncertainty principle does not allow that. If you actually calculate the uncertainty, if you confine an electron to the size of a proton, then that energy is bigger than the binding energy of the electron. So it can't do that. That's one explanation, is the Heisenberg uncertainty thing. You cannot confine an electron to such a small place without giving it so much energy that it leaves the atom altogether. Well, that's an interesting thing, is that the uncertainty in its momentum is bigger than the binding energy itself. A particle physics explanation is actually a better one. If you take an electron and collide it with a proton, you can actually make a neutron. The neutron is slightly larger mass than the proton, as it turns out, though, and decays right back down to the proton and electron. So energetically, it would require more energy to shoot the electron into the proton than we have available to us. The kinetic energy of the electron is not enough to combine with a proton to make a neutron, which is a couple million electron volts greater in mass, as it turns out. So that's a particle physics explanation. But I think more appealing explanation is Heisenberg uncertainty. That's why we have matter at all.